So let me record it. I am very sorry for this. Okay. Okay. Then you click save. If you want to record it by yourself, you record, but I just started recording. So here is the curves, guys. Okay, these are the curves similar to the lecture. And here is the Excel. Just check all. Wait for some time. And remove these redundancies. And I like always to, to renaming stuff. So this is ID when VGS equal to 2. So ID when VGS equal to 2. Then make a copy. This is ID when VGS equal to 2.5. Again, copy and paste, but makes it 2.5. This is ID when VGS equal to 3. Again, I'm gonna change it to 3. 3.5. And finally, oops, this is 4. VGS, ID when VGS equal to 4. Okay, and here is this guy is actually VDS itself, VDS. And here is a nice trick. You just click Shift, Control, arrow down. It will give you just the ranges that you want. Insert, and I like that one here. Okay. Okay. So this is ID when VGS equal to 4. This is ID when VGS equal to 3. Let's enlarge a little bit the. I don't need this guy. Okay. This is ID when VGS equal to 4. ID when VGS equal to 3.5, 3, 2.5. This is not 25. 2.5, and here is 2. Okay. So just 2.5. Okay. 2.5. Okay, so now we want to populate this table here, this guy. Okay, we know how to do. I'm sorry, we know how to do the theoretical stuff. Now let's calculate VDS from the measure it from the curve. So for example, let's take an here is, for example, this is the value at which approximately the current start to flat out to be constant. So here is basically the linear region. You know, guys, there is linear region and saturation region. Okay. Here's the current saturates. This is just like active region, but they call it saturation here. Here is the current saturates. Okay, and here is the current. In some point have linear relation with VDS. That's why they call it linear. Although it's not that linear because for that part, for example, it's not linear. It's very clear. It's curvy. Okay, it's a quadratic relation. But anyways, so this is basically approximately the value at which the current start to saturate or become constant. And if you see, guys, it's 1.5. So this is VDS sat measured. Okay. And let's do it. So at where is this guy? 1.5. So yeah, this was at VGS equal to 3.5. So at 3.5, VDS set theoretically is equal to 3.5 minus 2 equal 1.5. And from the measurement, it's also 1.5. So the error here is 0. Okay. The error will increase whenever you increase VGS. Okay, it's not a perfect relation, but you will see errors, much more error whenever you increase VGS. Okay, so let's, for example, take measure VGS or VDS set at VGS equal to 4. So here, yeah, at VGS equal, here is VGS equal to 4, and it's around 2.1. 2.1. Let's do it. So at VGS equal to 4, this should be 4 minus 2 equal to 2. And here is VGS set. It should be what? It should be, as we said, yeah, as we measured 2.1. So there is some error here, which is 2 minus 2.1 over the theoretical value, which is 2, and multiply it by 100 to get the percentage. Okay? And take here is absolute. So there is some error, and this error will increase whenever you increase VGS. It's not a perfect relation, but it's good enough to be used, which is VDS set equal to VGS minus V threshold. Okay, guys, it should be easy. It shouldn't be that complicated. So whenever you have a problem, just let me know. Okay? We have, let's say, 15 minutes. Okay?
Yeah, sounds good.
Thank you. So the transfer characteristic of NMOS is actually a relation between VO and V input. Okay. Many times this VO we need we meant by it VDS, and the V input is VGS. So we change VGS, which is the input, and we track the output at VDS. Okay. In our next lecture, I will explain in details how to get this transfer characteristic, but it should be something like this. Let's draw a circuit first, because again, this characteristic, depend on the transistor itself, the transistor parameters, as well as the circuit around the transistor. You can differentiate. You can't draw it just for the transistor. So what I am doing here, I'm just putting a source at VGS, and we have here VDD, and we have here RD. Okay, and here is VDS that we consider V output. So if we draw this characteristic, it will be something similar to what I will draw here. Here is V out, here is Vn, which is VGS in that case. Here is VDS in that case. It will be something like this. Then we have, some region, which, almost similar to linear, we can say. Then we have another region here. Okay. If we analyze the three parts we have in that curve here, this point VGS is equal to V threshold. This point I am calling all the time VGS set. What is VGS set? The voltage or the input voltage at which the transistor will leave the saturation region and enters the linear region. And we have three parts. In that region here, the first one, the current is 0. Why? Because VGS is less than V threshold. Guys, our transistor, will not turn on until VGS exceeds V threshold. Because at V threshold, there will be a channel between the drain and the source. Okay, without this channel, there will be no conduction, no current between the drain and the source. Okay. So if we apply this to this circuit, If there is no current, if ID here is equal to 0, then the voltage here V output, which is equal to VDD minus ID RD. If ID is equal to 0, then this will be equal to VDD. That's why here it's VDD and constant. When the voltage here, VGS, become V threshold and go beyond that, we go to the saturation region. So let's draw this. So number 2 here. This is the second region. Number 2. So here in region 1, the transistor is off or cut off. Just like the BJT transistor, if V input or VB less than 0.7, it will not operate. It will be off. Exactly the same here, but our 0.7 here is V threshold. And of course, V threshold will depend on the transistor itself. For example, in our transistor, it's 2 now. Okay. The second region is first ID is larger than 0. I mean, there is conduction. The transistor is on. And for that particular region, the transistor is working in the saturation region. In saturation region, VDS, which is V output, is always larger than or equal to VGS minus V threshold. Okay. Number 3, the last region here. So this is saturation. And the last region here is linear. Again, in linear, still ID larger than 0. Okay, and the transistor is on. But the transistor beyond VGS set, which is the point at which the transistor will go or transfer or go from saturation to linear. The transistor will go to linear. Okay, and here VDS is less than VGS minus V threshold. Okay, and again, if we go down a little bit, I don't know how to do that. Yes. Again, the transistor main application between linear and cutoff is electronic switch or the inverter driver, just like BJT transistor. Number 2, the transistor main application in saturation region is amplifier. Again, just like BJT. It's exactly like BJT. I mean, it's similar, not exactly like. It's very similar. Okay, but the conventions are, the terminology are different, somehow different, But we have mainly the same control sequence. Okay, so we're gonna get that experimentally, and we're gonna get VDS set or VGS set. I'm sorry, and this point as well. We should verify from the experiment that we moved from cutoff to active at VGS equal to V threshold, and we moved from saturation to linear at some particular value for VGS. Okay. In the next lecture, I will give you how to, I will learn you how to get this, theoretically, this VGS set. But for that lab, I will just show you the equation. So let's now go to the experiment itself. Yeah, so Here is the setup. Okay, we have here a resistor RD equal to 1 kilo ohm, VDD is equal to 15, same transistor, and we have VGS. Of course, this value 0.65 you can just ignore. I mean, in sweep analysis, usually we don't look at the individual values here. And we're gonna have a voltage probe here because we need V output, we need VDS. Good. So we have here also DC sweep. So we're gonna sweep this guy VGS from 0 to 6 and make this 0.05, not 0.1. Okay, so here it's 0.1, make it 0.05. And the output will be VO, the probe. Hit run, get the transfer characteristic, copy and paste from Excel to this guy, to this placeholder. Okay, now here is, the theoretical value for, VGS set and VGS, the one, that turns the transistor on. So here is VGS on, the one, the value of VGS at which the transistor turns from off to on or to saturation region. It should be V threshold, and you will find it's really V threshold. You may have some error with this guy, small error. So basically, you need to calculate first, VGS set from that equation. That equation is a quadratic equation. I'm sorry, there is a square here that I forgot. I am very sorry. So there is a square here. Oops, it doesn't let me do that. Because it's. Let me fix this very quick. So, need something. VGS in here, and here is a square. Yeah. Okay. So this is a quadratic equation. Okay. So you will have to, if you solve it, of course, RD, Kn. How to calculate Kn is from the model. Okay. I will show you now how. So Kn, RD, VGS is unknown, V threshold is 2, VDD is 15. Okay, this will have two solutions. This equation have two solutions. One of them is rejected because you will get two solutions. One of them is less than V threshold, and the other one is higher than V threshold. Okay, so we will neglect the one less than V threshold because the transistor is on. Okay, when the transistor transfers from the saturation region to linear region, it's on. There was a current. So VGS must be larger than V threshold. So the two solutions of this equation. One of them is less than V threshold. The other is higher than V threshold. So we'll pick the one which is higher than V threshold and put it here. Okay. I'm sorry. There should be only one. Yeah. So we get the one which is higher than V threshold and put it here. Then we measure it and calculate the error in both cases. So let's do it together. So I don't need this. Transfer characteristics. I already opened it. Yeah. Okay, simulate. Yeah, here is the value. Make it 0.01 or 0.05. And we click run. So this is basically VGS or V input, and here is VDS or V output. Here is the transfer characteristics. We need here two values. The value at which we start conducting, okay? So whenever you see VDS is equal to VDD, which is 15, you know the transistor is not conducting. So basically it should be, you know, this point, because this at that point, the transistor is still off, but once we get VGS go beyond this point, you know, we start to conduct, okay? So this point at which the transistor you know, become on, it's 2 volt, and we know that VGS should be 2 volt for the transistor to become on, to switch on, okay? So we should put here 2 VGS on theoretical. I'm sorry, this is V threshold. This should be V threshold. The theoretical value is V threshold, which is equal to 2, and from the measurement it's also 2. Now for VDS set, okay, if we do, I'm sorry, where is, yeah, if we do the equation here, it should be 2.53. Let me check very quick before I give you a number. Yeah, 2.53. So if you solve this equation, it should be 2.53. Okay, the other solution is 1.44, which is rejected because it's less than V threshold, which is 2. So we will pick this solution. This is the correct one. Now, the measurement. Okay. So it's here 2.55. Okay. 2.55. There is some error, although it's very small. Okay, guys. One last thing. So if you wanna, you know, solve the quadratic equation very quick, you can use this this one, this website. So let me share it with you in the chat. Okay, any questions?
Can you go over the switch and the amplifier part?
This one again. You want the tablet?
No, I'm not sure about number 5 where the NMOS acts as a switch and as an amplifier.
Number 5, you mean in the manual, right? Biتصف. What?
Yeah.
Yeah. So what is the range we can use NMOS circuit as a switch? Okay, just look at here. So let's okay, so okay, whenever the V input less than V threshold or higher than VGS SAT, which is 2.53 theoretically, or 2.55, we can use it as a switch. Okay, you know, switch needs high voltage and low voltage. So any voltage higher than 2.55 or equal to 2.5 will be considered as high, as high, and the output will be low. Any voltage less than 2, okay, will make the transistor off, and the output will be high. So that's the inverter drivers that I talked about in BGT. So this is basically the range for V input or VGS less than V threshold, which is 2, and VGS higher than 2.55, which is So for that range of inputs, the transistor can be used as a switch. Okay. For amplifier, we can use it, you know, in that range, in the saturation region, between this point and this point. So when VGS higher than V threshold, which is 2, and less than 2.55, you know, you can use it as amplifier. Okay.
Yeah, okay. It's exactly like the transistor from
BGT.
that's
Yes.
okay.
Yeah. Yeah. Like BGT, exactly right. Yeah. Okay, guys. So I will be with you until 12:30 if you have any questions, okay? Or, you know, anything.
Was this K value, was that the KP value on the model, or is that the width divided by length times the capacitance?
What is this KB value? Where exactly?
If you right click the transistor model.
KB value, okay. This one, right?
Yeah,
Is that
the value we're using? Okay.
Yeah, KB value is mu n COX. You know, okay. So let me do that on the tablet very quick to make it clear for you. So share the other screen. Okay. So you know, guys, ID equal to half Kn VGS minus V threshold square. This is in saturation region. And in linear, ID is equal to Kn VGS minus V threshold VDS minus half VDS square. This is in linear. So in both, we need two parameters from the transistor. One is called the Kn and the other is called V threshold. Okay? Kn is actually not one parameter. Kn is equal to mu n, the mobility of the electrons, okay, multiplied by COX, the capacitance of the oxide. So remember, if you go back to the structure of the MOS transistor, it's a metal, that's why it's called metal. Then oxide, that's why it's called metal oxide, you know. Then the semiconductor. So the capacitor here is not like normal capacitors. You have metal, insulator, then metal. No, you have metal, insulator, then semiconductor. Okay, that's why it's called the metal oxide semiconductor transistor. Okay, so COX is the capacitance per square meter of that capacitor between metal and the semiconductor. Then multiplied by W over L, the width of the channel multiplied by divided by the length of the channel. Okay, so KB is actually in multisim. This is called the KB, mu n COX. Okay, in that case, in our case here for 2N 2000, it is 20.78 micro ampere volt square. Okay, this is of course dimensionless. W over L is dimensionless because it's length over length or meters over meters, you know. Okay, Chris?
Thank you.